the formula for the automorphic correction of our Jacobi form capital Phi. This is the automorphic correction of holomorphic or weak Jacobi form of weight k for the lattice L. This automorphic correction depends on the choice of vector v, then it depends on tau, the first variable calligraphic z1, and the second small variable small z. By definition, this is equal to e to the power minus 4 pi to the square of the vector v, the quasi-modular Eisenstein series G2, then z small z to the square. Phi tau z1 plus zv. This is the automorphic correction. And now the main property of this automorphic correction is the following. Let us analyze the Taylor expansion of this function in that. I get the sum n greater or equal to 0. The Taylor coefficient f index n depends now in tau and z1, z to the power n. Then this function f n tau z1 are holomorphic Jacobi form of weight k plus n with respect to the lattice L1 if the original function phi was holomorphic, or weak if phi is weak. The proof of this fact is very, very similar to the case of one variable. Now you have to analyze the functional equation, so I leave this calculation for you as exercise. So first of all, you have to check that a tau plus b, you have to find the functional equation of this function, z1 over c tau plus d, z over c tau plus d. You have to find this using the functional equation for the original Jacobi form phi and to the quasi-modular Eisenstein G2, and then the same you have to do for any translation with respect to variable z. In the first case, a, b, c, d is in SL2z for any, and now for any vectors lambda and mu in the lattice L1, which is orthogonal complement of the vector v in the lattice L. So, and you get that this automorphic correction has the same transformation like the Jacobi form of corresponding weight for the lattice L1. So you see that in the case of modular form in many variables, automorphic correction gives us Jacobi forms. Jacobi forms for sublattice of corank 1 in L. So using one Jacobi modular form, you can construct infinitely many Jacobi forms for smaller lattices. So this is the main idea of automorphic correction, which is very, very useful in very many questions, especially about the graduate ring of weak Jacobi form and so on. And now I don't like to write the proof, because this is direct calculation. In the first and the second equation, you have to use only the functional equation. And please analyze this idea of automorphic correction, because you cannot find it in the book of Eichler-Zagier. Moreover, this fact about automorphic correction of Jacobi form in many variables, maybe, I don't know, maybe in my paper you cannot find it, and in other papers as well. So this is really, it's very simple, but nevertheless really new method, a really new formulation. And in the PDF file related to this lecture, I add some number of exercises related to this method. But now I would like to finish this lecture with classical formulas about theta function. So automorphic correction, maybe the last small section, subsection. Automorphic correction of Jacobi theta series, because the Jacobi theta series is really the main hero of our course. First of all, the first fact, you can find this in the literature. We have the following formula for the Taylor expansion of the Jacobi theta series. This is equal to 2 pi I z. We know that the Jacobi theta series has 0 of order 1 for z equal to 0 times the Dedekind theta function to the power 3. This is the derivative of theta series and z equal to 0. And then we have e exponent minus the sum 2 over 2k factorial, the summation of all k greater or equal to 1. Then we have the Eisenstein series G2k, for k equal 1, we have quasi-modular Eisenstein series G2, 2 pi I z to the power 2k. So this is more or less explicit exponential formula for the Taylor expansion of the Jacobi theta series. This is the first fact which I would like to mention. I'll give you explicit reference where you can find the proof. But the second fact is very, very important if you would like to understand not only the Jacobi theta series, but some other important special function related to this function. And now one can prove the following formula for the double logarithmic derivative of Jacobi theta series. One can prove that this is up to minus the Weierstrass p function plus 8p square, our quasi-modular Eisenstein series. So you can get the quasi-modular Eisenstein series as logarithmic derivative of the Dedekind theta function, or as the second, a part of the second logarithmic derivative of the Jacobi theta series. Rho, this is the famous Weierstrass p function, or p tau z. This is Jacobi form, meromorphic Jacobi form, of weight 2 and index 0, and this Weierstrass function has the following Taylor expansion: 1 over z to the square, so this function has a pole of order 2, times the sum k greater or equal to 2 pi I to the power 2k. This is like in this formula, but without any exponent. G 2k tau times z to the power 2k minus 2 over 2k minus 2 factorial. And maybe to fix all formulas, I remind you the Fourier expansion of the Eisenstein series G2 with G normalization. This is minus the Bernoulli number B2k over 4k plus the sum sigma 2k minus 1 and n q to the power n greater or equal to 1. So if you would like to understand the theory of special function of the theory of Jacobi theta function, please try to prove or to find in the literature, first of all, the formula for the Taylor expansion of this function, and also the formula for the double logarithmic derivative of the Jacobi theta series. If you can understand these two formula, then the Jacobi theta series becomes your best friend.